Number 1, how do the rate of a reaction and its rate constant differ? The rate of the reaction is the change in concentration of reactant over the change in time. The rate constant is going to be the same for the reaction regardless of the instant in time. The rate of the reaction can change, for example, as the reactants are used up, the rate of the reaction is expected to slow down. Number 2, doubling the concentration of a reactant increases the rate of a reaction 4 times. So if we have a concentration as 1, then that's going to equal some rate. If we double that concentration, then the rate is then multiplied by 4. So what's the order of the reaction with respect to that reactant? Well, that's going to be second order because it's 2 squared is how it changes the rate. B, by tripling the concentration of a different reactant, we increase the rate 3 times. That's a 1-to-1 relationship. That is a first order with respect to that reactant. Number 3, approximately the same question. If we triple the concentration, so if we go from 1 to 3, we change the rate of the reaction times 9. Well, 3 squared is 9, so that's a second order reaction with respect to that reactant. And B, if we increase the concentration by a factor of 4 and the rate increases 4 times, then that is first order with respect to that reactant. Number 4, how much and in what direction will each affect the rate of the reaction? There we are. If the rate law is as follows, so we have the rate is K times the concentration of NO2 squared. So if we decrease the pressure from 0.5 to 0.25, then we're reducing it by half. So half squared, we're going to reduce the rate by 1/4. B, if we increase the concentration of CO, that does not affect the rate, so it will not affect the rate. The rate will be the same. Number 5, we have this rate law here. The rate is equal to K times the concentration of NO2 times CO. So if we increase the pressure of NO2 from 0.1 to 0.3, we are multiplying it by 3 because it's a first order reaction. That means the rate will be multiplied by 3. If we increase the concentration of CO from 0.02 to 0.06, again, we're multiplying it by 3. So again, the rate will be multiplied by 3, and that's because the exponents here are 1s. Number 6, we're given a story, and we have a reaction that the nitric oxide plus ozone reacts to form this stuff, and we're told it's first order with respect to both of the reactants. So the rate is going to be equal to the rate constant, which is given 2.20 times 10 to the 7th, and that's 1 over molarity seconds, and it's first order with respect to both of those reactants. So this is our rate law. What's the instantaneous rate of disappearance of NO when NO equals this value and ozone equals this value? Well, we plug in the numbers that we are given. And we get in the calculator a rate that is equal to 4.28 times 10 to the negative 5, and that is molarity per second. Number 7. Again, we're given a story and we're told that the rate is equal to 4.85 times 10 to the negative 2, 1 over days, times the concentration of phosphorus 32. So what's the instantaneous rate of production in a sample of phosphorus concentration of 0.0033? Well, we're going to insert the values that were given. So 0.0033, and we calculate then a rate of 1.60 times 10 to the negative 5 molarity per day.